29. Using the standard entropy data in Appendix G to determine the change in entropy for each of the following reactions. All the processes occur at the standard conditions and at 25 degrees Celsius. Okay, so in this case, we have our balanced equation. We have carbon, which is the graphite version, right? It's a solid, it's graphite, plus oxygen gas, O2 gas, which will produce CO2. Now, we want to find the change in the entropy. A change is always that delta, right? And entropy is always going to be a delta S. So S for entropy, change, delta, triangle. So we're just finding a delta S value. Now, they did tell us that we're using standard conditions. So that means that we're going to be finding delta S notch. This notch, or like that degree symbol, always means that you're under standard conditions, which means that we can use the appendix values in the back of a book, right? The back of the textbook. So that's why they're saying go to that, in this case, Appendix G, to find out that standard entropy data for each individual component. And that's exactly what I did. So the entropy value for carbon, graphite, is 5.740 joules per mole times Kelvin. For oxygen, it's 205.2, and for carbon dioxide, it's 213.8. Now, from these values, we somehow have to find the change in the entropy. Well, there's a simple formula for that. It's this right here. The delta S for the whole entire reaction equals the sum. This little, symbol here just means the sum. And when we say sum, we mean that we're just adding, right? So we're going to add up all the products and subtract from the sum of all the reactants. So essentially, it's basically products minus reactants. So let me just pull this down a little bit here, and let's sum them up. Now, are these numbers going to be the same, or are they going to be different? Well, that's where the balanced equation comes into play, right? For each one of these values, it's always for 1 mole. But if I look at this balanced equation, there's no coefficients in any of these, right? Which means that I have 1 of each. I have 1 carbon, I have 1 O2, and I have 1 CO2. So each one of these would be the same value. But let's just say, for example, you have 2 carbons. You would have to times that carbon value by 2. But in essence, since all of them have a 1, I'm just going to multiply all of these by 1, which essentially is the same number. But I'm just showing you just to kind of get a system in place. Now, we have to sum up the products and the reactants. Literally, the balanced equation, it was carbon plus oxygen. So the 5.740 plus the 205.2. I don't have to add anything on the product side because that's the only number here. So I'm going to go over to my handy dandy calci, and I'm going to add the reactant side up. So we have 5.740 plus 205.2. Looks good to me. So the reactant side looks like we got, looks like the reactant side has 210.94. And the product side, since it's just the same, that's going to be 213.8. So here are my total values. Let's plug those values in for the delta S. So the change in the entropy, the delta S standard, that notch for the whole reaction, RxN is reaction, is just equal to 213.8. And I'm just going to minus the 210.94. Okay, let's see. Delta S for the whole entire reaction is, let's go back over here. Let's say 213.8 minus 210.94. And there you go. 2.86. And the units for the delta S is joules per mole times Kelvin. So J per M times L. Not L, Kelvin, right? Mole times Kelvin. And that's it. Seems like we're entering a positive entropy. We have a positive entropy change, which means that we're increasing our randomness or our disorder. So, yeah, cool. Thank you so much. Let me know in the comments if this helped you out. I really hope this did. Subscribe to the channel if you want to help us out, and I hope to be seeing you in future lessons. Okay, bye-bye.